Hey guys, I had a lot of questions on this problem, so I thought I'd make a little video talking about just sort of reviewing torque, because that's a good thing, and then also talking about how we use tension to find frequency and wave speed and all of that good stuff. So the first thing we want to look at is, you see that we have this bar of mass 45 kilograms, and you're going to want to draw that because that's going to be important for understanding what's going on. So here's the wall. And you have to forgive the background noise. I'm having a bunch of construction done on my house. So here's the wall. Here's a hinge, okay? And here is the bar. And we can move the bar where we want, and let's make it a little bit thicker. Okay? We know the angle between the bar and the wall is 30 degrees. We also know that there's a string that's attached from the wall to the bar, and this should be at an angle of 90 degrees. Okay, so we know that the bar, let's make it gray, the bar has a mass, let's say let's make it black, say the bar has a mass of 45 kilograms, and let's say the bar has a length of L. Okay, so that would be this. Alright, so we know that we want to find the frequency, and we know that there's an equation that has frequency. So we're going to start with that. So remember, wave speed is equal to frequency times lambda. We also know that there's another equation for wave speed, which is equal to tension over linear mass density. And remember, linear mass density is just mass over length. Okay, well, let's make this little m. So that would be the mass over length of the string, which we have different numbers for. So the mass of the string is going to be 0.092 kilograms, and the length of the string is going to be 0.33 meters, which is 33 centimeters. So this is for the string. Okay, so we have these things, and the key thing we're going to want to try to find here is tension. Okay, and in order to find tension, we're going to have to use what we remember about torque. And this is a statics problem because obviously nothing's moving. So we want to think about all the forces acting on this bar. And there's basically three forces acting on the bar. The tension is the one we care the most about, and that always points along the string. And this is a force diagram, but remember, we have to draw things on the bar because we're going to use torque, so it depends on where they're acting on the bar versus the hinge and all of that good stuff. So that's our first force. Our second force is going to be the weight. And remember, that acts at the center of mass, so that's going to be mg. And then there's a force here, which is the hinge force, but we don't really know what that is, so we're going to try to get rid of it. And the best way to get rid of it is to pick this part, this hinge right here, as our pivot, and so we measure things from there. So we have this vector, right? That's going to be, well, this length and then this length. So this is L and this is L over 2. Because remember, torque is equal to F cross R, where R is this length from your pivot point, or the distance from your pivot point. So when we sum up our torques, we know they're going to have to be equal to 0. In order to do that, remember, what the cross product tells you is that we need the force perpendicular to the rod. So in this case, we want to break up our our forces into parallel and perpendicular components to the bar. So like this, okay? Now when you're looking at this angle is 30 and this angle is 60, but then we have a t cosine 30, and then this would be t sine 30, but we don't actually care about that because that component isn't going to be part of the cross product, okay? And then this angle should be 30. So this is going to be mg sine 30, when this is mg cosine 30, but once again, we don't care. We only care about the perpendicular components. So when we actually write our f cross r, right, we're going to start with t cosine 30. This should be positive, because remember that would rotate it in the counterclockwise direction, which is positive for rotating things. And then the r is L. So here's our force perpendicular, here's our distance from our pivot. Okay, remember we picked the pivot not just because that's where the hinge is, but also because we wanted to get rid of this force that we don't know the angle for. All right, and then we're going to subtract off this other torque, which is going to be mg sine 30, and then L over 2. Oops. We'll make that purple. And when we sum up all these things, it's going to be equal to 0. Okay? And you'll see we still just want to find torque. So we're just going to solve for t. You'll see the L doesn't matter even though we don't know what it is, because it's going to cancel. And you end up with torque is equal to 1/2 mg tangent 30 degrees. And when we plug things in, this is 45 kilograms, 9.8 meters per second squared, tangent 30, and that's going to give us 127.3 newtons. So we found our tension. That's it there. And now we need to use that to find frequency. But we know we have these other two equations. So we plug everything in, and we're going to find the wave speed, which is torque over linear mass density. So we take 127.3 newtons over 0.092 kilograms divided by 0.33 meters, and that equals 21.37 meters per second. So now we have our wave speed, but we still need the frequency, and we know that this is also equal to, this speed is also equal to lambda times frequency, so frequency is equal to wave speed over wavelength, so that's 21.37 meters per second. And remember the wavelength, if we have a standing wave on this guy, the first fundamental looks like this, which means that's only half a wavelength, because a whole wavelength would include this part. So that means the wavelength is double the length of this string, so 0.66 meters. And that means that our frequency is 32.4 hertz, which it turns out is in the range of human hearing, so you would be able to hear it. And that's part B.